order when counting. 1, does order matter? We should say, does order matter? Sometimes that's clearly stated, and sometimes that's implied just in the setup of the problem. The second thing is repetition allowed? So whatever it is that you're using to count things, can you reuse those things? So one example where repetition is not allowed is maybe like you're playing Scrabble, right? And you have so many letters and you're putting down letters onto the board. Well, once you put down a letter, you can't use it again. So that's an example where repetition is not allowed. This is one of the bigger kittens. He is probably 14 weeks old. Okay. What did I say? Oh, yeah. So a case where repetition is allowed might be a password, right? You don't use up the letters. You can keep using the same letters over and over and over, right? So the thing that you're using to count, can you reuse them in the counting? That's a repetition. All right. Now, before we go on and start addressing these, here's a tool that we all need to make sure we're on the same page with, which I'm guessing most of you are, but let's just do a review. All right, so for any non-negative integer, n. So what's the difference between non-negative and positive? Zero. Yes, 0 is included in the non-negative integers. It is not included in the positive ones. So for any non-negative integer n, I'll say n is greater than or equal to 0 for clarity. We define n factorial denoted like this by n factorial equals n times n minus 1 times n minus 2 all the way down to 2 times 1. And that's if n is greater than 0. That's how we define it for the positive integers. I did want to be able to define this for all non-negative integers. This definition, this expression up here doesn't make sense for 0. So we're just going to go ahead and say that by definition, 0 factorial will be 1. Okay, so note that a mathematical definition is not a truth, it's an agreement. We've decided that this is the properties that we're going to include in our definitions, and we're going to go forth and prove things, say things, conclude things based on this definition that we agree upon. Okay? Is everybody familiar with factorial? Okay, let's just make sure that we can manipulate it pretty well. So let's start basic. 4 factorial, that just means 4 times 3 times 2 times 1, right? Well, 3 factorial is 3 times 2 times 1. And hopefully what you see here is, I could write 4 factorial as 4 times 3 factorial, right? Hey, 2 factorial is just 2 times 1. I could have written 4 factorial as 4 times 3 times 2 factorial, right? So I can always pluck off however many factors at the top, and then wherever I stop, the rest of it's the factorial of that, right? Everybody's with me on that? So if I had something like 4 factorial over 3 factorial, that's 4 times 3 factorial over 3 factorial, or just 4, right? What is 4 factorial over 2 factorial? Don't say 12. Don't say 12. They'll tune me out because it's too easy. TikTok. 4 times 3. What about n factorial over n minus 1 factorial? N, good, right? Because I could write this as n times n minus 1 factorial, and those cancel out. What about n over n minus 2 factorial? What's that equal to? N times n minus 1. All right, last one. What about n minus 3 factorial over n factorial? Good. It's 1 over n times n minus 1 times n minus 2, right? So if you've taken Calc 2 or BC Calc, you would have seen factorials and actually had to manipulate them somewhat when you work with sequences in series, okay? If you haven't had Calc 2, maybe you would have seen it in pre-calc. Where have you all seen it if not in Calc 2? Anybody know where they've seen it? Discrete math. Discrete math, you would definitely have seen it. Good call. Thank you. Yeah. Has everybody had discrete math? That's not a prereq, is it? It's not a prereq. I think a lot of people, if you're a math major, CS definitely would have had discrete math. Okay. So we're going to need factorial in our counting. So we're just going to store that. That's one of the tools. Also, one more thing I want to state for us in math, which you all should know, but in math, or mathematics, we should be more formal. In mathematics, did you know in almost all countries, oops. Where's my green? I lost my green. Turned different color. Okay, there we go. In mathematics, the or is an inclusive or. Everybody know what that means? It's not really how we talk, but it is what you always assume in math unless otherwise stated. So what that would mean is, so A or B translates to A only, B only, A and B. So any of those satisfy A or B, right? So that's the part about the inclusive or. Okay, so those are our tools. Now let's see some other things that we need to keep in mind when counting. And that is, so you would have done counting in discrete math for sure. Permutations and combinations. All right, so we'll go breeze through these. So sometimes you're going to have to make choices, an exclusive or, and sometimes you're going to be completing steps. Like you're going to do this and then do that and do that, or you're going to count things like that. I'm going to first do this, count it, and then do that, count it, and then do that, count it. So when you have steps, those are like your and. So this and then that, you're going to multiply. Like maybe you go to an ice cream store and your first step is to pick one of 31 flavors. And you can only have one. And then your second step is to pick a cup or cone. And your third step is to pick only one of 3 toppings. Okay? So you can think of it like a tree, right? 1, 2, all the way down to 31. And then for each choice that you make on flavors, you now have to choose cup or cone, cup or cone, cup or cone, cup, or cone. So at this stage, I should have 62 possible things, right? The flavor and then a cup, or the flavor and then a cone. And then for each one of those that I choose, I get to pick one topping. So I have 3 more things, and that happens at each one, right? And so I think we can easily understand why we're multiplying when we do steps, right? So the total number of scenarios I could come up with would be, first of all, the flavors, then the cup or cone, then the topping. What is that? 686 total possible scenarios. That's if you're doing steps. Like when we count cards here in a little bit, counting full house, all that kind of stuff, we will be doing steps. But we also will have to sometimes make choices. And let's talk about the exclusive or. So if we do one thing, then we don't do the other. Sometimes we are doing things and the way we choose to count has to address the fact that we're overcounting. So we have to be careful. So if we're doing choices, it's like we're going to count all the ways if we do this, and then we got to count all the ways if we do that. Together is all the ways we do it. We would add them, right? We don't multiply them because we don't and, we exclusive or. Okay? And in this case, we add. Like kind of here. So in our first step over here, we had 31 choices, right? And really, if you ask how many ways could that happen, we'd add up all those choices, which are 31. And if you choose the first flavor, you don't choose the second. Or if you choose the second, then you know what I mean? And so forth. So if we are performing choices, then we add. If we are performing steps, then we multiply. And then let's just formally state that generalized principle of counting. Okay, so if our experiments or steps that are performed in such a way that the first experiment step may result in n sub 1 ways, the second in n sub 2 ways, and so on. Then, there are n1 times n2 times and so forth up to n sub r possible outcomes.